Now back to the Gauss-Markov assumptions. I want to look particularly at the last one. So the assumption that the errors at different time points are independent of each other. In other words, there's no autocorrelation. Now, it turns out that in fMRI data, errors actually are autocorrelated, meaning errors at different time points are not independent of each other. So instead of the covariance, if you take the covariance between any two errors, instead of being zero, it's some matrix V. Right? In other words, the residuals are not distributed as a normal 0 and sigma squared identity matrix, as they should be, but they are distributed as a normal with mean 0 and variance sigma squared V. And V is a V correlation, or the covariance, over different time points. So when autocorrelation is, when there is autocorrelation, the variance covariance matrix not only has sigma squared down the main diagonal, but it also has non-zero off-diagonal elements. And each of these elements tell you how much two time points are correlated with each other. For example, this is telling, this number here is the amount of correlation between time point 1 and time point 2. The next one would be the amount of correlation between time point 2 and time point 3, et cetera, et cetera. So these correlations ought to be zero, but in fMRI, actually, we know they are not zero. Now, the problem with residuals being correlated, so the problem with autocorrelation, is that the estimator itself, the beta, remains still unbiased. What changes is that the variance estimate, that becomes biased. And on top of it, therefore, you get your actual degrees of freedom are less than the nominal ones. Now, this can affect you differently according to what kind of autocorrelation you have. See, if you have positive autocorrelation, meaning if the error at each time point is just a slight variation of the prior error, so if you have positive autocorrelation, then what you're doing is you're underestimating your variance. Now that means that your t-tests will be artificially much larger than they would be. And in fact, for a nominal 0.05 test, you could actually be at 0.16. Now, you get the exact opposite if you have negative autocorrelation. Now, this is when the value, when the error at each time point is the opposite of the error at the prior point, so where there's a sign flip across the mean. In that case, you will get an overestimate of the variance. Therefore, your denominator in your t-test will be larger. Therefore, your t-test will be artificially smaller than what it actually should be. Now, in the case of fMRI, we're typically talking about positive autocorrelation. So R probably is typically one that the variance the variance of the estimator, so the denominator of our t-test, is typically underestimated, which means our t-tests, our t-values, are actually artificially inflated. Now, how do we address this? Well, there are two strategies. There are two things that we typically do. First, and we already spoke about this, the high-pass filter. And second, we correct for the autocorrelation. And historically, there are two ways of doing this. One is called pre-whitening and one coloring. We will focus on pre-whitening because I don't think anybody does coloring anymore. So, as I said, the first step in fixing autocorrelation is to use a high-pass filter. And we already discussed this. And we already discussed how SPM does this by trying to model slow drifts, as you can see here, by adding them to the regression as nuisance variables or as regressors of non-interest. Whereas FSL goes into the data and tries to extract the actual slow drifts that are in there and removes them from removes them from the data. So here is where we had left it. This is our D-gamma convolved, or rather double gamma convolved boxcar regression. So here we are, and now we're going to apply high-pass filtering, and we will do this with the strategy of FSL. And you can see here, right, if you look at it, and if you carefully look at the time series, you can see that what happened is that the leftmost part of the graph, of the time series here, kind of got pushed up in a sense, right? It's easy to see if you look here at this point and down here. Whereas the end of the time series kind of looked like it got dragged down, right? So probably what happened is that the signal, there was a slow signal that might have been low here, and then slowly might have kind of gone up. And so what FSL did is it went in there, it found that slow frequency, and it kind of adjusted. If you know the trend was a little bit up, so it took this part here and it pulled it down. It took the first part and it pulled it up a little bit. In other words, it removed a slow drift. And if you focus on the values down here, you will see that our estimate has gone up. In this case, the variance goes down. And overall, the t-test goes down. And it's fine. It's just now it's a valid t-test. The number we had earlier was actually invalid because our variance was biased.